All right, everybody, welcome back. We're going to start looking at an application, if you will, of the normal distribution again, but this time we'll be looking at the sampling distribution in chapter 8. Okay, so I'm going to start to share the screen for some written notes, some information there, and we'll go into some practice with these calculations using StatCrunch and see how that compares. All right, so for this information in chapter 8, we're talking about the sampling distribution, right? And so now what we're kind of looking at, and it can be extended to different parameters, different values that we're computing for a population, okay, taking different samples. But basically here we're looking at the distribution of, I'll say statistics, right? Values we compute from samples. Okay, the distribution of statistics we compute from a population. I'll say that information, right? And so in particular, we're going to look at, right, our sampling distribution of sample means. Those values X bar, and we'll look at the distribution of sample proportions, these P hat values, right? So the proportion, like that percentage of a sample or a population later that have a particular characteristic, so on. Okay. And so looking at that, remember what we're kind of comparing to back in chapter 7, when we're looking at kind of like our distribution of, I'll say, kind of these individual data values. When we're looking at, right, those test scores from the entire population, or we're looking at the amount of money spent by different households for some particular groceries, or I think we did an example in the last video talking about how much garbage, trash was produced, right? Whatever it might be, or the heights of people, so on. And so in those cases, when we're doing those problems, and again, looking for those probabilities, I kind of imagine having all of our little particular data values, building up that distribution, and we started to see, okay, definitely right around that mean, that expected value, what we kind of anticipate a lot of our population having these values. So each dot representing a person that we've taken this data from in our population, so on, kind of filling in those. And of course, what we're hoping for in chapter 7, okay, was that this distribution was normal, that it had that bell shape to it, okay? And we had that bell-shaped curve going on with our data, okay? And so then what our discussion is now, instead of having this kind of calculation, trying to find that probability for an individual picking out of that group, okay? Let me kind of zoom in a little bit, make that look a little bit clearer, hopefully, okay? Is that now in chapter 8, what we start to see with these sampling distributions, now we're going to consider the distribution of those statistic values, right? Our X bar, our P hat, those sample proportion, right? So basically here, our values computed for all possible samples of size and whatever that is, right? So maybe we're going to take, for our population, we're going to take groups of like 15 students at a time and calculate their average, right? The average amount of money they spend on textbooks for a semester, the average number of hours they work each week, number of hours they're spending studying for a quiz, exam, so on. right? And so for each of those samples, you can imagine then building up this distribution. So here I have my number line here for these different possible values of X bar, right? So these are the sample means. And if you start to calculate, we can imagine, okay, for this first group, my X bar sub 1 is right there, right? And that first sample, its mean is in this value. We can put some numbers there if you wish. But then I calculate my second mean. My second sample has a mean like up here, right? Our third sample, X bar sub 3, a little bit higher, X bar sub 4, maybe somewhere in between. And so the idea is that we start to kind of build up, just like with our individual data values from before, from the population. Now, though, as we start to build up, we're going to have all these different sample means. And again, we can kind of start to see them stacking up and just generically placing all these little X bars as we go along. So now, instead of having those individual X values, if you will, now we're going to have these sample values that we're starting to accumulate. We can do the same idea with proportion P hat, okay, those sample proportions. And now we're building a new distribution, a new kind of curve that hopefully, depending on some characteristics that are discussed in this chapter 8 discussion, right? If our sample size is bigger than 30, then we can assume that that sampling distribution will be normally distributed. Likewise, if the original population was normally distributed, then the distribution of these sample values would also be normally distributed. So it shares that same shape. But the key difference, the key characteristic that we're going to kind of use and kind of need to discuss with our calculations, looking at that sampling distribution, is that we're going to need to alter, we're going to need to shift the standard deviation we use. Okay? And so here, kind of what our central limit theorem discusses. Kind of boiling this down, is that for our central limit theorem, as we start to go through taking these samples from a population, hopefully the population is normally distributed. That's going to allow us to use our normal distribution calculations again, or likewise our sample size n that we have for our sample that we're going to use is bigger than 30, okay? That our central limit theorem says that, well, we can use that normal distribution to compute our probabilities again. The probability that a value, our sample value now, is greater than some quantity, less than some value, in between two values, so on. We can use those normal distribution calculations, right? But we need to adjust or alter, recompute, right? The standard deviation. Okay, so now we need to make this adjustment, this recalculation for our standard deviation. Okay, but here, one key point, the mean will stay the same. Okay, and we'll see that in relationship to our proportions as well. Okay, but looking at this information, in particular when we're trying to deal with a sample mean, the distribution of sample means, okay, one of the key statements we'll look for is that we're looking for this probability that the sample will right, have a mean greater than, have a proportion, that the proportion for that sample will be less than, right? So we're looking for this key detail that we're talking about a sample instead of just an individual. We'll talk about that with some of our example problems in a moment, okay? But now, when we're looking at our sampling distribution, for the mean, right, our distribution of sample means, okay? The mean, mu, of all those sample means, mu sub x bar, right? So the mean, the average of all those sample means, we actually see that it's exactly the same as the population mean. For all the individual data values, when I start to accumulate the distribution of all the possible sample means x bars, the middle of the curve, that peak, right, is going to be the same as the mean, the peak, where our individual population data values were, which is good, right? And so then for our standard deviation, though, our sigma for those x bars, this is our adjusted standard deviation. We're going to take the individual population standard deviation, sigma, and we divide that by the square root of our sample size. And so in our calculations, we'll see, right, we'll typically get some long decimal value here, right? And in our calculations, what I'll mention, what I want to enforce is that in your work, right, show how you choose to round, right? You could keep the entire decimal value, so you would type that out for me or write that out for me, or maybe you round it 2 decimal places and you show that, right? So on your papers, and we'll do this in an example, show how you're choosing to round that for the calculations, okay? I'll say for your calculations, all right? And we'll see that in the documentation as we start to write out our process, okay? Now, on the other side, when we start to look for our sampling distribution, right, this distribution of our sample mean, proportions, pardon me, right? So for proportions, what we're going to start to deal with in this case is that our mu, our mean, for those p hats, for those sample portions, is going to be equal to this value p, which is our proportion for the original population, right? This proportion, this percentage of our population that has a particular characteristic, right? That maybe we're saying like 68% of our MPC students transfer after 3 years, right? For the entire population, so our P would be 0.68. And now if we start to take, okay, well, what if I look at this sample of 25 MPC students? What's the probability that the proportion of those 25, right, that proportion is going to be less than 50% that transfer after 3 years, or whatever it might be, okay? Our standard deviation for our sample proportions is this big square root, this square root, p, our population portion, times its complement, 1 minus p, all of that divided by n inside the square root. Okay, and again, as we go through, we're going to show how we do our rounding, right? But in our work in this chapter 8, we're going to calculate these probabilities for a sample using our normal distribution, but adjusting, changing that standard deviation that we use, okay? So, for example, to go through, and again, I'll kind of bounce between this and StatCrunch in a moment. I have this practice set. Again, I'll put this on our Canvas page to follow along as well. But looking at this problem, so sampling distribution, a local grocery store found that the amount customers spent on groceries was normally distributed, right? So this is kind of giving us that clue that we're going to be able to use our normal distribution with a mean of $135.79, right? So there's our mean, there's our mu for the population that they're spending this amount on groceries with a standard deviation of $24.68, right? So there's my sigma for the population, $24.68, okay? And so we'll keep track of that information. So now in this first part of the problem, reading it through, if a customer is randomly selected, what's the probability that that customer spent more than $150? So in this case, what's important to identify is that here we're just taking a customer, a single customer, right? So in this case, we're looking at the probability for an individual, for just one person out of that population. So this is just going to be our chapter 7 work, right? Just our regular normal distribution type problem. So a good little bit of review here. We want to find the probability that that person spent more than $150, right? So we're looking for the probability that that one person, that X value, that they're spending more than, greater than $150 on these groceries, right? So that means we're going to go to StatCrunch. Okay, we're going to go to that StatCrunch, open that, and go to our stat, then our calculators, then go down to, right, our normal calculator. We're going to set that up. We have our value for the mean, right? Mu was equal to 135.79. Our standard deviation, $24.68. I'll leave off my dollar symbol, of course. And we're looking for that probability that X is greater than or equal to $150, right? That or equal to is not going to make a difference, right? So on StatCrunch, we're going to go and input this information and let's see what we get, right? So let me share my StatCrunch. And again, you can access that through your Pearson. MyLab Mastering through Canvas. Likewise, on our Canvas page, we should have the link. Okay. But looking at our StatCrunch, right? We go stat, calculators, normal calculator here. And now for this problem, our mean, $135.79, 0.79. Our standard deviation, $24.68. And we want the probability that X is greater than, right, more than $150. We can put 150. I'll put the change 0.00, computing. And so now with that information, our result here, right, our unrounded answer, our unrounded decimal solution from that screen, 0.28 238 538. A lot of 8's going on there. Now, for our probabilities, most commonly we were going to round to 4 decimal places, 1, 2, 3, 4. That 8 tells that 3 to round up. So for our rounded solution, our rounded answer, this probability, 0.282, that 8 rounds up, 0.2824. Okay. And no, that's for the individual, right? One person being selected, the probability, right? One customer being selected, that I check out their total maybe more than $150. We have a 0.2824, right? 28.24% chance of that happening. So now as we go to the next problem, keeping track of that same population that we're drawing from, now we're going to take this sample. And now that's where we want to pay attention. Now we're dealing with a sample of 24 customers. So now we're looking for the probability for a sample that we're going to pick 24 customers at random. Was a probability that that sample will have a mean amount spent greater than $150. We saw that $150 mark, right? But now we're looking at this sample mean to be greater than that amount. So we're going to look at this probability that our sample mean, that's that X bar, not just X now, so even our notation changes, that's greater than, more than that same $150, right? So anytime we're dealing with a probability for a sample, we need to adjust, we need to change, alter the standard deviation. And so now, with our adjustment, our sigma, our standard deviation for those X bars, the population standard deviation, sigma, divided by the square root of our sample size, and I'll have that stand out. Okay. And so let me switch screens real quick. I've been typing in that little box. Let me switch to here, right? So looking at that probability for a sample, right? We're dealing with the sample, n is going to be equal to 24. Okay. The probability for that sample mean, X bar, more than $150. Anytime we're talking about the probability for a sample, that sample is being brought up, we need to adjust the standard deviation. The population standard deviation, sigma, which we call, I'll just do the numerical value, 2468. We're going to divide that by the square root of our sample size, the square root of 24. You can calculate that square root of 24 individually, or this time, again, I'm going to share the document camera. Let me do it this way with, or sorry, not document, with my computer screen. Let's share it like so. Okay, so we have our calculations. I'm going to switch over to Desmos real quick. The scientific calculator. We can calculate the square root of 24 first and do that division. 24.68 divided by that long decimal, 4.89, 89,79486. Well, hopefully I didn't make any mistakes in my typing. Or with Desmos or a scientific calculator, graphing calculator you might have at home working on this, we can do that division all together. Make sure I don't mistype, like I said, though. There we go. Dividing that by the square root of 24, right? That same long decimal result, this 5.037783904. Okay. And this is where I mentioned we can make a choice for how we round. In this case, right, this is what I'm going to type into StatCrunch, as you'll see. I'll round this to 2 decimal places, let's say 5.04, right? So if I take this, I'm making the choice to round to 2 decimal places. This is going to be the value I'll use in StatCrunch, okay? So again, in StatCrunch, when we do our calculations, using a normal distribution calculator, our value for mu, the mean, stays the same. X bar, right, same as our population mean, $135.79. But now, our standard deviation, we're going to use that 5.04. If you want to write that long decimal, you can. Type in that long decimal, you can. Just show what value we're using. And again, we're talking about trying to find this probability that our X bar greater than $150. Okay. So now in our StatCrunch, we should be able to see this screen. Going back to StatCrunch, same mean. Now we've adjusted our standard deviation, 5.04. Still greater than 150 we're looking for. Compute. And now notice how that probability got extremely small, right? Because now we're trying to just, instead of just finding an individual value that's bigger, now we want all these customers, these 24, to kind of coincide, to match up, to be part of this group that's greater than 150, right? And I always kind of compare it, like if I'm trying to make plans with my friends, getting a bigger group of my friends, 24 customers, right, to sync up, to align is going to be pretty difficult, right? To get them all to agree, have similar values is not going to be common. So that probability will starts to get smaller in our calculations. So doing that work, right, our unrounded solution, our unrounded answer, taking from StatCrunch there, we can see 0.0024, 0.534. And if we want the rounded version, as usual, rounding to 4 decimal places, 0.0024. Extremely small, very rare, very unusual for us to get a sample in that range. Okay? All right. And again, we could draw that picture as well, kind of help mimic that flow that we did back in chapter 7, but it's kind of getting into the calculations, hopefully clear. You can always double check that normal distribution video to recap that drawing, that use of our normal distribution curve, that bell-shaped curve, as we've been doing, okay? So now, looking at this last part of the problem, this last example. So now, what if we're going to take a sample of just 18 customers now? So again, that sample of 18, we start to see we're going to deal with a new sample size, 18, and we want to find the probability that the sample mean is going to be at most $125, pardon me, right? So now we're looking at the probability for a sample. Our sample size has changed. So we're going to have to readjust our standard deviation that we're going to use, okay? In this problem, we're looking for the probability that our X bar at most, right? So that's the most we want to spend. It's not going to be greater than, it's not going to be bigger than. We're not going to spend more than 125. So now we're going to switch this over less than or equal to that $125, okay? And truthfully, that less than or equal to, or just strictly less than, calculation-wise, is not going to make a difference, right? Some of that wording, right, we'll want to keep track and be careful here. But now, for our adjustment to the standard deviation, right, our sigma sub x bar, the standard deviation for this new sample, C, okay, is going to be our population standard deviation, still the same as before. Now we're going to divide by this new sample size, and we'll just keep track of how we round there, okay? And so we put my placeholders in. Our population standard deviation, $24.68. Our sample size this time, 18 people, 18 customers. And so if I switch over here, doing that, $24.68 divided by square root of 18, there's that 5.8 that I tried right before, 5.817, 131787, okay? And again, just out of habit, I'm going to round to 2 decimal places. You can choose to round to other places if you desire, right? But maybe because I'm talking about money, 2 decimal places make sense, the dollars and cents there. And so then on StatCrunch, right? So in our work showing how we're calculating, identifying these values that I'm typing in, the StatCrunch, our mean, $24.68, that's staying the same. Sorry, I'm getting my standard deviation. I just made my mistake there. That was $135.79. There we go. Our standard deviation better. There's that $5.82. Okay. that 2460 was the original population standard deviation. And then now we're looking for that probability that our x less than or equal to 125.00, right? And so now, truthfully, it should be x bar. I'll write it this time, right? But on StatCrunch, it just shows up as x, which is fine. That's the variable being used. Same mean, 5.82 for our standard deviation. We want to be less than, switching that inequality, 125.00, computing, and now we get this unrounded result, unrounded solution, 0.03187.302. And then we round to 4 decimal places. We're going to get 0.031.123 in one more spot. That 8, the 7 rounds us up, so that's going to go up to 0.031. Okay, slide this up so you can see that on the screen better. So now there's our probability that when you pick a sample of 18 customers, that their bill is going to be at most $125 for that group of 18, 0.0319, right? About a 3% chance of that occurring, right? 3% of those values for our sample means of all 18 samples, right? Or 8 samples of size 18 customers we can build. Just 3% are going to be in that range below $125. Okay. All right. So then with those, we're looking for that probability for a sample mean, right? That was that distribution of sample means. Okay. Now we can also look at our distribution for sample proportions. Okay. So now looking at this next example, a study by the National Pediatrician Association found that 44%. Again, when we see these percents, we're thinking proportions. Okay, that percent is giving us a proportion. So this national study, right? So now we're looking at all the population. 44% of 7-year-olds drink carbonated drinks daily. Okay, so that's kind of identifying that our value for P, that population proportion, 44%, and we always work in decimals, 0.44. So now we're going to take this sample of 80, right? So there's our sample size, N is going to be 80 7-year-olds. What's the probability that at least 40% of those 7-year-olds, right, in that sample drink carbonated drinks daily, right? Have this characteristic. So in this case, we're looking for our probability that this P hat, that our sample proportion, right, is at least 40%, right? So that means that it's going to be 40%, at least 40%, 40% or bigger. So that means we're going to be greater than or equal to that 40%. But again, we're going to work in decimals. So we're looking at the probability that our P hat greater than or equal to 0.40. Okay. More than 40% are going to drink carbonated drinks daily. Okay. And so now in this case, our mean mu for those P hats is equal to our population proportion. That was at 0.44. So that's the middle. That's what we kind of expect to find with all these different samples. Okay. Our standard deviation, though, we're going to find by taking this big square root, placeholders in, numerator, that proportion P, times 1 minus that proportion from our population, that mean value divided by n, the sample size. So in our set of values, we're going to take that population portion, 0.44 or 0.44 times 1 minus that 0.44, all divided by 80 this time for our sample size. Okay, and so in our calculation, doing that, big square root, I'll put my fraction inside that division, 0.44 times, parentheses, 1 minus 0.44, close that parentheses, we're dividing by 80, our sample size, and we're getting a really small standard deviation. But again, common with our proportion, we're getting 0.05549 77477. Okay, and for me, I'll round to 2 decimal places again, p hat there, and call this 0.06. But again, we could round. If you want to keep 3 decimal places, we can do that. Up to you how you calculate. Just wanted to make sure we show it. And so then in StatCrunch, doing our normal distribution calculation still, right? We're going to go to Stat, Calculators, then down to normal, right? Our mean, that proportion, 0.44, our standard deviation, sigma, we talked about is 0.06. Or again, you can write that full decimal if you wish. Now we're looking for this probability. It's going to say x, right? We're talking about the sample proportion. We want it to be greater than or equal to 0.40, right? So this is the same thing. X greater than or equal to 0.40, just so you see on the screen. So now we start to put that in. Our mean, 0.44. Standard deviation, 0.06, that rounded value. We want to be greater than 0.40. Notice that's below the mean. So our starting of our area is going to be to the left of the mean and over, computing here, right? So there's our mean will be that 0.44 in the middle. Now we're taking this full probability, so we're getting a big portion of that area. So that's why you get a large probability there. Okay, and so now doing those calculations, our unrounded solution for that probability, 0.74750746. Our rounded solution, rounding at the 4 decimal places, 0.7475. Right, that 0 less than 5 stay the same. Okay. All right, so I'm going to take this off for a second so we can see this page a little larger, right? So in our work, we're taking this probability for a sample. This time, this probability that our proportion, this percentage, right, for that sample, at least 40%, so 40% or bigger, so we're doing the greater than, adjusting our standard deviation, the square root, population proportion times 1 minus the population proportion is complement. Other place you might see is called Q for that 1 minus P, okay? All divided by N, that sample size that we have. And now our standard deviation that we're going to use in our StatCrunch calculations. We could write that long decimal to show me what you're typing in, what you're using, and we can evaluate. All right, so one last example just to get some practice with this sample proportion distribution. The Chancellor's Office of the California Community Colleges, okay, stated that for all community college students, 68% complete their transfer level math course during the first 2 semesters in a row, right? During that first year, basically. And if we see, we're hoping to get a majority of our students to complete their math requirement, right? Like the stats class. So in a sample of 95 community college students is selected, what's the probability that less than 60, right? That we're not getting enough students to complete their transfer level math course in their first 2 semesters. What's that chance? What's that probability, right? So in this case, from the entire California community colleges system, for all of those, right? So there's our population, all it says that 68% complete the transfer level math, right? So our value for P for the population, 68%, or as a decimal, 0.68. Now we're looking for the probability that when we look at a sample of 95, right? So there's our N, 95. And we want the probability that less than 60%, right? So in this case, for the sample, that P hat was a probability that that's going to be less than 60%, right? Or that probability P hat, the probability P, right, of our sample portion P hat less than 0.60, okay? Since we're talking about a sample, we need to know our sample values. Our mean, the same as our population portion, 0.68. Our standard deviation that we're going to adjust, sigma sub p hat, that fraction or big square root outside. Let me get that. Sorry, I know my writing a little messy. P times 1 minus that proportion P. There we go. All over N inside that square root. I'll do better about writing on this side. Square root. Put my placeholders in. Filling in. Population portion 0.68 times 1 minus that 0.68 divided by our sample size, 95. Now I'll start to share screen again, sharing my Desmos calculator. Back to that screen, right? Big square root, fraction inside, population portion 0.68 times parenthesis, right? 1 minus 0.68. Close that. All over. Sample size 95. Enter. And again, with these values, with this set of data, I know my decimals get kind of small. They're not necessarily always this tiny, but just with the examples I built up. Our unrounded value for the standard deviation, 0.0478594433. And so my rounded value, again, this time just to be different, let's round to 3 decimal places, let's say. And I'm going to say, okay, approximately 0.048. Okay, and again, we can do 2 decimal places, you can do 3, just as long as we show those values we're using, I'll be happy, okay? And so in this case, that way I can kind of confirm the same result I get or different result. StatCrunch, we're doing that. Stat calculator's normal distribution calculation, our mean, 0.68. Our standard deviation, 0.048, that rounded value I talked about here. Now we're looking for a probability that our sample proportion less than 0.60, right on there. If you want to call it X, you can jump back to that, less than or equal to, right? So now going to our StatCrunch calculation, our mean this time 0.68, standard deviation 0.048. Now we want to be less than, not 0.40, but 0.60. Computing here, and we're getting that tail, that portion, right? So for our unrounded solution, we're getting here 0.04779 0.035. For our rounded solution, we're rounding to 4 decimal places. Our common convention for these probabilities. 1, 2, 3, 4. That 9 rounds us up. 0.0478. So there's that probability, that likelihood that if we took a sample of 95 community college students, the probability that less than 60% had completed their transfer level math in their first 2 semesters, this 0.0478, right, 0.0478, that probability of basically 4.78%, which is kind of good. That's unusual. Maybe that means that definitely, as the chancellor's office suggests, that there's going to be typically a higher proportion that have completed their transfer level math in the first 2 semesters, which is what we're hoping for. Get in, get that math done, so that way it's out of the way and you're on your progress to transferring to your next institution. Okay. All right. But there's using that standard deviation adjustment, so that way you can go into our normal calculator on StatCrunch to evaluate. Okay. So in our work in chapter 8, dealing with these probabilities for samples, the sampling distribution, okay, instead of just the individual data points, now thinking about X bars or P hats stacking up. And anytime we're talking about the probability for a sample, using that sampling distribution, we have to adjust the standard deviation. All right, folks, that's it for this one. Questions, let me know. Otherwise, take care. See y'all soon.